Okay, let's start. Okay, today we are going to, I'm not going to teach too much. I'm going to let you guys do coding and try some experiments using what we have there on the Jupyter lab. I mean, I'll go through some things first, and then a lot of the class today will be sort of lab work, where you can get to try, well, hopefully you can try some things out and then have some fun with the code, okay? I think that's the best way, because for the next assignment, that's what you're going to have to do on your own. But we're going to try it out today in a lab. We're staying on the Hopfield network, and we're going to try out different ways of making the Hopfield network or using it, you know. And essentially the assignment, that's what the assignment is trying to get you to do. So like making your own Hopfield network and then like trying it out in various ways. So today we'll kind of practice that in the lab. In the class, and you can ask questions, and you can work with each other, and then hopefully today's session will give you some confidence, so that when you go back and you program your own thing, it makes sense to you rather than being lost, like what's going on. Okay, I think that's the most important thing. And so to help you along the way, I have kind of from last week what I've done. Sorry, the last class, which is 2 weeks ago, I've added kind of like a streamlined version, and I'll go through that. A streamlined version of the code steps that we went through last class. And so today I will be going through that with you, so that you can use that as an initial platform and then kind of evolve from there. And then to try to address some of the challenges which I've listed in the Jupyter notebook. So before we start, there's a couple of administrative things, okay? First, the assignment, the homework 1, so everyone's got their grades, and you can see that, I don't really, it's basically either you pass or fail, you get the 10% or you don't. And everyone gets the 10% because they handed in something, okay? And everyone did decent work, so I have no issues there. Although, I must say that there is a common thing that I realize people don't really grasp. I don't think this is a too serious or a fundamental problem, but I think it's just a matter of being used to the kind of, it's to do with notation, okay? So I did put it in the email. I sent it to email because I do not want it to be on a public NTU Cool site. The solution for homework 1, I assume you guys all got it, right? You should have gotten the email, and you can see the answers for homework 1, or at least the recommended answers for homework 1. And just to highlight that, I'm not going to show it on this because it's recorded, but if you go to the answers, you will see I think the key common problem that most people have is actually the first question, okay, of the homework, which is this one. Okay, write this vector equation in the above is scalar form in vector form. Okay, and in vector form, because you all start to do the whole matrix, or different people have different answers, but none of you were right. A equals big C and then B, okay? That's actually very simple. That's the vector form, okay? So the answer is actually very simple. It's simply that A is equals to sorry, not W, but should be C. And the C is uppercase, and the B is lowercase. Uppercase being the matrix array, and lowercase being like it's a vector. So if you want to qualify, you can actually do this. That these are vectors, okay? And that the +5, because it is a scalar, then is simply just +5, okay? All right? This is just a notation thing. You can even add a dot here if you want to say that this is multiply, right? A dot product of the array with the vector, okay? And that's it. That would be the 标准答案, okay, correct answer. Because everyone started doing things like, wow, C, I, B, I, C, Y'all start doing this, okay? I mean, it is sort of the vector, expanded vector form. Yes, not wrong there. But what we are looking for is like to express it in simple notation. The reason is because when you write papers, let's say simulation papers, when you communicate the formal mathematical ideas, okay, you can't be writing the whole array out, right? So you have to know, be confident about using these vector forms or these mathematical notation conventions, okay, to communicate with other scientists or to transmit your ideas in a very crystallized, efficient, and precise forms. Okay, any questions about that? But other than that, I think everyone got it in the sense of the idea. So this is just a matter of, like, I think, style and getting used to the meaning of what it means to go between arithmetic and vector form. Okay? So I don't think y'all have problems. It's just basically to show this to you, and then you'll have, like, you'll get it. Okay, so let me see. Let me go back to the... Yes, clear. Okay. Okay, so that's just that one thing about homework 1. Any other issues with homework 1 that people had and want to raise? So I gave you the answers. Please go back and look at it yourself. I mean, you all got the marks, but some of the details are worth comparing. Okay. Now, homework 2 should be due today, this evening. If you haven't handed it up yet, please hand it up this evening. Okay. And if you have issues, like you can't hand it out on time, just email me. Let me know. I'm happy to just give a little grace. It's fine. Okay, I'm not too particular about it. But again, it'll be the same thing. Homework 2 should be like a pass-fail issue, but you can, kind of make sure that you understand the concept. That's the important thing, okay? All right, and so then today, after you hand up homework 2, you should then be worried about assignment 1. Okay, and let me pull it up here. And just so you know, so that you can also get the idea of what you should be getting out today so that you can then go and do assignment 1 on your own, okay? So assignment 1 asks you first to build a Hopfield network, as I said, and then it will ask you to kind of break it or try out various things, all right? So we can go through it a little bit later, all right? But today's class will be more of a lab thing to gear you so that you can have some hope of doing assignment 1. Okay? All right. So on that front, any other administrative or logistical issues with regards to the course, the homeworks up to today? Or any other topics or conceptual, theoretical things about perceptrons, Hopfield network, that we have dealt with in the past lectures? No? All good? Okay. Then in order to get us started today, I'm going to have you guys maybe to set up, okay, each of you have a computer screen to work with because today we want to do some lab work, and I was thinking that maybe what would be helpful is if you guys can connect to the screens, and then if you do some work, the other people can see also, and it'll be nice, a collaborative atmosphere. I'll do this experiment. I've never done this before, and I figured that the future classroom is good because you can do that. All right. So I've put the connectors for you on the tables. If you guys can take a look at it, open the boxes, and there should be HDMI cables in there that you can directly hook your laptop to, adapters. Or if you need, you can use the future classroom Wi-Fi thing. Let's see, 我们有1, 2, 3, 4, 5, 6, 7. So 我们可能就只有6个. So maybe one person have to switch and share 这样子. There's 2 more here. And when they say 左右, I don't know 谁的左谁的右, so you just give it a try. 那前 means there, and here there's another one here. So 前排 means 前中后. Okay, so you can like spend maybe let's spend about 10 minutes or so, 5 minutes or so to see if you can try to hook up your computer to that, and then I'm going to like change this mode so that the screens should be reflecting your own output. Let me see. No, I believe you guys can control it yourself. Oh yeah, yeah. I think you guys you can like if you do the double tap, or when you connect it up, you should be able to just directly hook up to your screen, and then see if you can kind of project your laptops to it. Yeah, we take about 10 minutes to figure out this logistics. 可以吗？有问题吗？ You all can share it too if you want. 诶，没有，前面应该有诶。你需要装那边吗？那个。Ooh. This mysterious technology. Yeah. Yeah. So today will be very like dynamic and interactive and more fun, I think. Okay. It's not going to be just a one-to-all lecture, more like a lab, and I think that's better. 可以吗? I thought we tried it the last time, didn't we? And it worked, right? We can project from, at least from the phone, we could project to the screen. Yeah, well, obviously we could do it from the laptop, right? No? I'm doing this because then if you guys do coding, you can share and look at each other's much more easily. And then, don't need to sit at your own seat. You can walk around and look at other people's, and then copy each other's code if you want. 这个可以吗? Maybe 你用那个离开这边有一个 PC， 等一下 ，Let's see， 这是你的吗？哦，不是，这个 PC 是这个电脑的 PC，so let's see，let's go home， 资讯源 ，this HDMI。哦 ，OK， 那 I think tap it。这是你的吗？这是我的。OK， 可以。So， 没有，哇，这是什么？资讯源，然后这边有 HDMI 点，然后有装了吗 ？OK，then 等一下它好了，你就可能点它 ，just tap it。Yeah, there you go. And then wait. 慢慢来 ，you just gotta give it time. OK, great. 这是你的吗？OK, there you go. And 这边可以吗 ？Double tap. 哦，你要用这个啊？你没有 HDMI 吗？用 HDMI 也好。 还是那个方向不对？
没有，这个是那个吧？这是可以，
这是可以用，不过对无线是可以用，只是 I was a little bit confused how to do the 无线，and I forget how to do it. 哦，对啊，其实 you can just turn around, right? You don't have to. You can sit like this. Yeah, maybe makes more sense. And what about you? You have issues? 这边可以吗？来 HDMI， 你要不要转过来？对对对，你可能坐这一排。哎，那边后面也有一台哎，你们没有要用？那边还有多一台，so that you guys don't have to squeeze through. You can，你可以这样子做啦，比较温暖啊 ，OK， 没有问题。Yeah， 哎，有更长的吗？那个很短的感觉。Yeah，why？ 是可以用这个无线分享的啦，but I oh where is the longer one? This one？ 这边有吗？哦，哎，有，来，试一试比较长的这个。怪，因为它这边接着，它另外一边是倒反。对对对。OK。哎，为什么不进去了？
因为它这个太短了，它这样要插，我的在这一边。啊哈。所以我想用这个，但
对啊，
好像就它就没有讯号。
那你要用那个无线什么什么的这个。啊，你这边要用那个 Future Classroom WiFi。
是
Edu Room 的那个。
有，现在是 Edu Room。
OK，and then 好像有一个要选那个 TV 什么的。So I think there is a， 诶，没有说吗？它好像有一个说明书。Is there something there? Why don't you try this one then? Try this. Yeah, if you are adventurous, you can try the 无线的方法 and then we see if it works. And 无线投影。
这样才是无线的。
不是，这样透过这个就是无线了，它就不是用 HDMI。对，你可以拔掉。
我以为它是一个转。
不是，这个是无线的意思。对，try that and then 无线。有吗？让他说什么？你可以点他，给他一些时间。OK。Power on， 插进去。哦，你要连这个 SSID 要这个，所以你找那个 SSID。WPSQPMR， 你如果用无线的，你需要有这个资讯。This setting on top。可以吗？如果那个很短，这个你用的长的嘛，这个是长的。OK， 好。And feel free to move the table around. You don't have to like the table. 如果说那个桌子你可以调一下比较舒服，就直接挪一下，反正它是有轮胎。轮子，轮胎，可以吗？
我直接转一边就。
哦，呀，直接转一边。这边说好像你有连接嘞。 它有 detect 到一个。哦，是不是？哎，没有啊。对啊。啊，OK 了，好了，这样就直接用 HDMI 是最稳定的。这个这边对，资讯可以吗？这边可以吗？
因为它的没有，它没有 HDMI。
哦，那你可以用那个无线的。那无线的你要回去到那个刚刚那个。无线是这样。你点那个资讯源，对，资讯源。然后如果用无线杰荣你看一下，你无线需要连这个，它等一下会出现那个。对，有一个密码跟那个 SSID。有，那个 SSID 是这个那个上面的。但如果你有连的话，它就会有一个1。then 你就可以用这个方法，1跟2这个方法。是这个 SSID 吗？好像还没有。哎，你有 register 吗？
有啊，因为他叫我承认，是 Future
Classroom。Yeah，Future Classroom 吗？
然后是
ED Room 的。哎。对对对，如果他要用无线，就要接那一台。哦，哎，没有 Mac 的话，理论上 Mac 的就不用 ，Mac 就直接用那个 AirPlay， 就是他如果连 SSID， 理论上那个 AirPlay 就抓得到了。Right? For Mac OS, it should be like very quick, but he has to have his EduRoam set up. Yeah, it's AirPlay ready. So if you go to your Wi-Fi and you connect to this SSID, you should be able to just turn on your AirPlay. I think you have to turn on your AirPlay. Yeah. So I check if people are okay here. 这边可以吗？这边有了， then 这边有了，这边有了。Okay, if you have, please go to today's the Jupyter Colab that is on the modules homepage. And then you can take a look at what I have on the screen there. So the main screen here will be my screen, okay? And you guys have your own stuff. And you should navigate to this simulation 2 and take a look at simulation 2 making streamline evaluation module and take a look at what I've done here, okay? So if you for those of you who have set it up, okay? No rush, okay? It's going to be messy and dynamic today, so we'll figure it out and we have time. And yeah, you go to the home, okay? And then scroll down to this week is April 11. Go down to the syllabus. Sorry, down. Scroll down. No. Go back to home. Go back to home, and scroll down. 滑下去，再下去。And 在 week 8，不是week 6的 binary， 这个对，就点它。OK。等一下。Okay. And you should also have your own Jupyter, lab instance or Jupyter Colab open. But scroll to simulation 2. If you scroll to simulation 2 below, go down. Okay, yeah. Take a look at here from simulation 2 onwards. Or if you forgot previous weeks, you can take a look at the ones above as well. 所以这不行吗？ 你的
不知道要怎么弄，
你要用 HDMI 吗？
但是因为它太短，所以我只能接这个。
它有长的，它有一个长的，
没有，两个都是短的。
是这样。
诶，
对，
对，
他也没有跟我们说，早不说这样子，每次都是这样。I do think that 它的无线的连接是可以的，只是那个真的很复杂。Yeah, it's like it's as if they want to give you the ability but not give you the ability, and then like it's just like last time they have, I don't know if you are do CD player music right? 它包装就是很封得很细。It's like you buy the CD and then it's like you can never get it out. It's like they want you to listen to music, but they don't want you to listen to the music. This is the thing that we always complain about last time. 所以这边不行吗？它的OK， 那你
我在重点是 EDU room。
Okay, I think the key thing is EDU room. If you can get in EDU room, then that can work. Yeah. Okay. So, but in the that's just for projection. In the meantime, on your own laptop, obviously you can see things, right? That's just for projecting and sharing with everyone, as and when we need to. So, 那这边 OK 吗？ Is that your screen? You hook up HDMI, right?
Yeah.
Let me check real quick. Home. 诶，对。你是不是有 double screen? So make it mirror 是吗？这好像是你的。
No, PC screen.
Mirror. 是教室的，你可以用。对，你可以用。对，我不用，你可以用。That's true. Yeah, 那个可能会比较快。Yeah. 是不是你的这个 HDMI 的那个
Because it's detecting something, but that
Yeah.
something is nothing.
你有用过吗 HDMI？
有啊。
OK。
有了。也可以啊。呢，刚刚有 flash 的东西。OK， 好 ，Great. All right, does it work? Okay, great. Awesome. So now we are really using the future classroom. Otherwise, I don't know why we need the future classroom. So many screens. All right. Okay, so as I said, if everyone's connected, everyone has their own sharing screen. It's very cool, okay? And the point here is that you are coding and you can interact with each other, and I can also see what's going on for everyone's screens. And I believe I can also, if you are working there and you want to project here, you can or I can pull the screen over to here as well. And that way we can like really kind of dynamically use the classroom. And so today's class will be focusing on using the autoencoder Jupyter Lab that I've set up and we've gone through last class. And the first step that I'm going to do is to show you like all the things that we did before for the autoencoder briefly. Then I will show you that I compile it into I organize it into a more like user-friendly interface, all right? And then kind of like play with it a little bit, and then there will be some challenges at the end that you can use and you should use and see if you can solve it, all right, on your own. And I do have to warn you, I do not have solutions, okay? I know that there should be solutions, but I haven't worked it out because the point is for you to work it out, okay? And then have fun and share it with everyone, okay? All right, so hopefully we'll get it done by today, by 12, by lunchtime, that we will all have some confidence in being able to code an autoencoder from scratch and then kind of use it, okay? I think that's really the point we want to transmit today, okay? And that today is the last day we will be sort of dealing with autoencoder in the classroom because next week we will move to backprop, all right? And so today will be the key for you to be able to pick up things to do the assignment. All right, so let me just revise very quickly. You can read it on your own, but you can see that this is the Jupyter notebook that we went through the last class. The idea of autoencoder or Hopfield network is to do content addressable memory. Content addressable memory meaning that the key test of content addressable memory is that if I encode tokens into this network, okay? If this network encodes it, just like a human, if you give humans a list of words or a list of items, or absorbing and perceiving the environment that is filled with different things, different objects, different scenarios, okay? That if when I probe you, I test you, so I give you partially some episodic feature. So like this room, this episode, is being encoded in my brain, okay? Then next time somebody asks me something like, hey, how many lights were there? Was this one of the lights, the shape of the lights that you saw in the classroom? That is a partial cue. And this partial cue, when you kind of test the network with it, the network is able to re-instantiate the original entire episode. And that is content addressable memory because you address that memory trace using part of the content, okay? So that's very brief. We've talked about this over and over again. Hopefully this has been burned into your brain. All right, and Hopfield did it using, the principle that Hopfield used was to build this kind of node, all right, where you have a fully connected node in which every node connects to every other node except itself, okay? And in this architecture, embedded in this architecture is that the weights, how the weights are kind of structured or learned or updated is according to the Hebbian rule. The Hebbian rule meaning that, you can see here, this is the Hebbian rule instance, okay? When you train or when you encode information into the network, it encodes it into its weights. The weights of the network are changed according to the Hebbian principle, which is that if two things are alike, okay, if this node and that node are firing similarly, then our weights will be strengthened. And if you are not firing but I'm firing, so if we are different, then our weights will be kind of dampened. Or if you are not firing and I am not firing, that's also similarity, right? That's also being together. So that will also strengthen the weights between us as well, okay? And that equation or that function is instantiated in line 29 there, okay? I hope you all can see. We went through the formulas before in the theory part. And then not only that, you have the architecture, you have the learning rule, you also have the activation function. In this case, this is the regularized binary linear unit. Okay, if it is above a certain threshold, U, then it will be a 1. The activity of a node will be 1. If the summed weighted inputs are less than the threshold, then the activity is 0. Okay. Here's a kind of a challenge also, maybe for you guys to consider. In this case, it's binary. It's either fully 1 as an integer or fully 0 as an integer. You might consider something more smooth, like the sigmoid shape, okay? And if you do, this is where you want to change it. You want to change this to a sigmoid function. All right? And then you can play with it. All right? Okay, so, and then other than that, we also get a bit of the other metrics like the energy of the system, and using Hamming distance to see whether the system is activating and reach a stable point where it's no longer fluctuating. We'll see this being played out more later on. Okay, excuse me. So that should go through what we have. All of that, all this you can go through in the other details. So that's what we have tried out to work through the model. So today what I've done is I have, we are going to do simulation 2, okay? So let's call all of that simulation 1 to pick up those principles in bits and pieces. Now simulation 2, we're going to integrate everything together to make it into one easy to use or easier to use, all right, module, complete module, because we need that, because if everything in bits and pieces and if we want to try out different things, it becomes very messy, very difficult. We always want to integrate it so that it's a module, so that then we can use it in many different applications, okay? So this is a style I want you guys to pick up. At first, when you are figuring things out, you break it apart, and then you figure out how these things work, what they mean. But eventually, you want to clean up your code so that it becomes very streamlined, because you figure it out already, so you don't need to worry about the connection. You got it right, so you know your code. And then now you want to clean it up so that it becomes easy to use. In other words, you want to package it, okay? Now, this is not just for this class, but in general coding principle, right? When you do coding, maybe you work with it, it's messed up, but at the end, when you figure it out, you should package it for yourself, because then you can use it in many different applications. Plus, you want to then be able to share it with others. Other people can use it because you've packaged it nicely, all right? If you didn't, then like when you want to share it with other people, they can't figure out what's going on in your head, right? So this is the packaging part, okay? So simulation 2, we are going to package things, make it more streamlined, and then we're going to see later on if we can use it, the packaged version to apply it. Now, disclaimer, I didn't spend too much time packaging. Things can always be made even more and more efficient, but what I've done is just kind of semi-step of the way, enough for us to use it in class, or at least in lecture. Okay, so what I've done at first here in the streamlining is to first, actually, I don't know, this is redundant. I guess I can remove it. I can take it out, I guess. I don't need that. Okay, so definitions. So what I've done here in this the first step in putting things together is I went through to look for all the definitions that I have. Definitions meaning preset functions that I define on my own, okay? And so for example, one of the definitions I had is to be able to visualize the node, all right? So that was one of the things we did before. I just cut and pasted it here, okay? So that it becomes an easy to call function, and I modified it a little bit. So I called this function graph the Hopfield network of k nodes. So I give it a parameter so that I can make it different size, right? I can make it 16 node size, I can make it 8 node size, I can make it 64 node size if I want, okay? Very cool to play with. So then this definition, next time, all I need to do is call this function and tell it how many nodes I want it to graph, and it will generate that fancy node architecture visualization accordingly, okay? This is just to visualize, all right? So this doesn't have anything to do with the computation at the moment, but you can imagine that you might be able to kind of use it to do some computation because it uses the networks toolbox. Networks toolbox actually generates a graph object, and the graph object itself can be used to do neural network architecture programming. Another definition I have is the original training or encoding the Hopfield network with specified weights. Maybe your weights is preset to 0 or some pre-trained weights, and the input token array that you want it to encode. So you have the architecture defined, W, and what you want to encode in this architecture, A. Okay? So the brain and the episodic information you want to put into the brain. Okay? So that's all put into a nice, neat function. And I put it into the comments here that this function will return a W. So if you run this function, you can put this function is equals to W, and the W will be the trained brain, the brain that has been trained on A. Okay? And then I also have the testnet Hopfield, which I will call retrieve. Okay? And what this will do is it will take the trained weights, okay, the trained brain, and some testing input that you want, the partial input that you want the brain to retrieve, and then some other hyperparameters, which includes the number of iterations where you count before the brain has settled. Okay, in terms of retrieving, because it's thinking, right? So do you want it to give it a long infinite response window, or do you want to only give it like 2 seconds, you know, just quickly, whatever you retrieve, give it to me. So this is like giving it kind of like a time window to respond, okay, how long you want it to respond. And then this is, other hyperparameters would be U. Activation threshold is now a parameter. So I say that, hey, this network, if you want it to be very fair, then U is set to 0, okay? But maybe I want it to be very, like, maybe I give it a shot of dopamine or something. So it's very easy to activate. Or I give it a shot of, I don't know, I give it sleeping pills, so it's very drowsy. Okay, so I can play around with this parameter as well, so that I can see, hey, if you're sleepy, how do your memory work? You know, if you're very hyperactive, how does your memory work? So I can give it this parameter as well. Also, remember in the original testnet Hopfield network, we only pick one node at a time to activate, to change the activity, okay, if you recall. So the standard is n of I is 1, all right? Just update one node at a time. But maybe we want to also make it so that maybe it updates more than one node at a time, and then we see how it works. So I give this the option as well. So I modified, I copied from the original testnet Hopfield definition. When I streamline it here, I open the capacity for me to also modulate U and N of I. And you can see that U is here, okay, that's the threshold. Originally, I set it to 0, but now I've made it a parameter that I can call in the function, I can set in the function. And originally, the number of nodes is just 1, but now I've made it so for I in range of N of I, so if N of I is 1, then it's equivalent to before. But now I can say 2, right? If I say 2, then it can maybe update like 1 node, and then maybe update another node, or maybe update 3 nodes or 4 nodes, etc. Okay? So I just modified it a little bit to give it this capacity, and this is the testnet or the retrieval function. Okay, any questions? Okay, then the other things are just visualizations and some other utilities. So for example, I want to visualize the weight heat map, which we did before. So this is the code for that. You can take a look. I want to visualize the energy curve time course. So this is the plotting function. I want to visualize the Hamming distance of this network as I update each node each time before it settles. I want to see how many times it updates. Maybe it's flipping back and forth all the time, or it just flips one time and then it's settled, okay? This should be tied to the energy as well, obviously, all right? So I want to visualize that, so I've made a plotting function for that as well. And then I also want to visualize the node itself as it does the retrieval. When I give it a partial Q, at first it's maybe very noisy, but then after a while it retrieves the trace and then it settles. It realizes it's correct, or it is hallucinating. It's just completely wrong and it doesn't even know it's hallucinating. Okay, so this heat map of the changes, AD is activation differential rather, okay, or activation derivative if you want. And that's A delta, okay, for me. And so that's a new kind of visualization tool I embedded here, okay? And then I have the distorting patterns as well, so I can distort the test pattern I want, so it becomes the partial input, not the original output, input, sorry. And then the reporting function, so like, you know, what do I want to see to evaluate the performance of the network. So all these are the definitions that I need in order to compile this module. Okay, so this is the way I work. So to do that, I can just run this so that it will load up the program. It will load up this kind of set of tools or set of definitions you need to test the network. Any questions about this? This is how I do the streamlining, all right? Many different people have many different ways, but this is one of the ways. Okay, if no problem, then how do we streamline? So we've streamlined the definitions. How do we streamline the application itself to use these definitions? And if you see here, what I've done is I've built a form. Google Colab is very easy because you can just define forms just by going here, the 3 dots, and you can say add a form, okay? And or you can say add form field. And for every form field you add, right? So let's say I do a variable name and I can call it a string. If I save it, there will be a form item here called variable name, and it will be like when you type whatever input here, that will be equivalent to the variable name in the code itself. All right, so that's how you use this form, okay? And you can either use the right-click graphical way of adding forms, or you can just know the syntax. And the syntax is like this. Okay, so see, you just, as long as you paste something of this syntax, Google Colab will know that, oh, you actually want a form in the graphical version, okay? Wow, today is very active. What's happening? It's a lot of like announcements today. Okay, so yeah, so you can set up the form this way. And the key here, why we want to use form is that because then it's easier to interact with it, right? I mean, you can interact it in code, sure, but I think we're still very visual creatures. So as long as you have these kind of inputs, it's easier to work with. And this takes some thinking because you need to project like, okay, what kind of things do I want to visually have and set? What are some things, no, I want it's just hard fixed, so I don't need to have it as a form, okay? So for me, in my app, in my Hopfield app, I've set up a form field where I can specify the input, the memory items that I want it to learn, okay? So that would be A. A would be the input array. And then I can set it also that do I want W, the weights, to be recursive? What recursive means is that it can learn from the previous weights. So maybe I have already pre-trained a weight and I want it to just use that. Or, no, I want it to just use the initial setting. So I just want it to use a scalar 0, okay? So right at the start, I haven't learned anything yet. I'll just say, no, I don't want it to be recursive because there's nothing to recurse, okay? But after having trained it once, maybe I want then to have the option to, no, don't set it back to 0. Use what you have and learn some more, okay? So this is an option. And then, do I want it to even learn anything? Or as in like, maybe I already have a pre-trained weights and I don't want it to learn at all, whether recursively or resetting it to 0. I just want it to use something that I already have, okay? So then this is, in other words, I just want to test. I don't want to learn at all, okay? So this gives it the capacity to say, no, I don't want you to do any learning. I just want you to do some testing, okay? All right, so generally we want it to learn first, okay? So this is the default for me, would be like, at first there's no recursion. Yes, I want it to learn, and I want it to start from the setting of a scalar 0 for all weights. And if you see how these three are used here between lines 25 to line 31, okay, you can see that, sorry, not the visualize. What this does is that if recursive is no, then use the W0, which is the scalar weight. Okay, so recursive is no right now, so you will use this one. If recursive is yes, and learn is yes, then use the recursive W. All right, use the weights that have been trained before. Okay, or else if learning is no, doesn't matter, then the W is a set W. Okay, so if recursive and you want it to learn, it will learn a new set of weights based on given weights. If you don't want it to learn, it will just fix the weights. Okay, so that's what this kind of if loop conditional allows us to play with. Okay, then the rest are like when I want to test, which pattern do I want to test? Pass pattern 0, and how much distortion do I want, and how much time do I want to give it to give me the answer. So this is the number of iterations to settle. Okay, and these are just, this one is a visualization for the heat map. Okay, I think for me, I will set it to 4. Okay, and then the number of nodes I want to update at a time, which is 1. And the threshold, which I set to U. So these are the hyperparameters. These are visualization parameters. These are other simulation parameters that I set. Okay. So and this one is the Walsh functions that I've set. So to make it even more pleasant, you can hide the code of the app, and then you can just play with the inputs. All right. So let's see. Hopefully it doesn't give me an error. Please don't give me an error. All right, it gave me an error. Yes, because not enough values to unpack. I need to give it, what am I missing? U, N of I. Give me a second here. U, N of I, T. Oh, right, of course. There's no R here. Okay. It seemed to like it. Okay. Some R error there. All right. So now my app works. Okay. So I've trained my network once on the Walsh functions. Okay. The Walsh functions as you see here. Okay. I've trained it once. And this is the weights. This is the weights which we went through last week, and you can see the pattern is as expected, right? Okay, there's this nice diagonal where it's the most distant, because it's Walsh functions, right? The most distance kind token is dampened for a given node that likes that token, okay? But then nodes that are like itself are like enhanced. And then, wow, this is serious. Oh, I pressed accidentally. The person today is very, like want to share news with everybody all the time. Okay, and the input that we wanted to test was this one, this Walsh function. We distorted it so that the partial input we gave it was this one, okay? And the output was this one. So apparently it couldn't really find the original answer. So it had a Hamming distance at 3. And you can see this is the network, how the network activity went. And if you look at this, probably the energy is flat all the time. Yeah, it didn't really change, okay? So in this testing instance, it seemed like it settled on a Hamming distance of 0, and then it couldn't change anymore. So this is a random instance where it didn't really work very well. Let's try one more time. Okay, again, well, didn't really learn very well. That's maybe because our distortion is set to too high, right? So we want to change it. Let's see. And it will update. Now it's doing better. Okay, let's try it again. Still 1. Let's see if we can get it to 0. Oh, something up with my code. I have to go and look at it. Okay, but here we go. Yeah, this is a case where it goes to 0. All right. So from maybe I changed a bit of the code too much, and I can take a look at it later. But the idea here is that it will, you can now use this app, okay, to then modify and play with the nodes, the activity, the weights, and like the input and the distortion and all that very efficiently, and then you can evaluate the code in a more systematic way. Okay, so any questions about this? Just the streamlining part first. Okay, so if not, then what I'll do is we're going to take a short break, and in this time, and when you come back, you can continue. What I want you to do is create your own Jupyter notebook, okay, or Jupyter Lab or Jupyter notebook, okay, separate instance. You can feel free to copy my code if you want, all right, and paste it there, and you should, because then you modify it there, okay? And then we're going to try the next thing, which is a statistical evaluation, all right? Actually, let's try doing number 2 first. That will be a bit more manageable, okay? Then after we do that, then we want to try it to encode 4 different inputs. So to this point, we have told the brain to encode Walsh functions. Now let's get the brain to encode non-Walsh functions, okay? And that will be the challenge for the next part of the class. So to do that, you need to set up your own Jupyter Lab and get working, and then maybe I'll give you guys about half an hour or so, okay? We'll be working, and then let's see where we can go, where we can get, okay? Based on the code I've given you. All right, so we're gonna take a break, and you can have your free time for about 30 minutes from now, and then we'll come back, and then we'll see where you are at. All right, any questions? Any issues or problems? Okay, if not, then feel free to just work on your own, and we'll check in again in about 30 minutes. All right.也不一定是上面这边。Yeah, so one issue is if you copy it in your own Jupyter notebook, bear in mind it is your instance. So maybe you have some settings or some things that are not the same as the way I set it. And obviously, you can't just copy and expect to use my version in that sense. You have to know your code, like what are some specific settings that you used, okay? Otherwise, it will complain, all right? just a small update is I realized there was a bug, as always, because when I added the ability to select more than one units to update at a time, my loop was a bit loopy. So I've updated the loop so that's correct now. So what it is like I can choose n of I, like if I want to update one unit at a time, so then if this n of I is 1, then I will be one random integer, and it will choose node I to update. But if n of I is 2, maybe I update 2 nodes at a time, then I will be an array of 2 numbers. So then for k in I, for the nodes, the first node in the array I, update that node, and then for maybe the second node, that's the kth node in array I, update that node as well, and so on and so forth. So now I've made it so it's correct. Previously it was not doing it correctly, so now this is okay. All right, so now the definition for retrieving testnet Hopfield has been updated accordingly, so just bear that in mind. I think it works now, so yeah, it seems to be behaving sort of normally. You can see this is the kind of profile you want, that it takes some time for the energy to go down. There's fluctuations in the Hamming distances at each time, and you can see that the nodes at first are like having different levels of activity that changes, and you can see it's to do with the Hamming distance, that there's a switch, so there's a Hamming distance uptick, and then there's another switch, and there's another Hamming distance uptick, and each uptick of the Hamming distance is associated with a drop in the energy level until it kind of stabilizes. Okay, so this is how you evaluate the network transition as it goes. All right, so then I will now test my app using some other setting, and we'll see how it goes. All right, so just this update. Yep. looks like people are still working at things, so we'll keep going. It's okay. It's good. We have some time. Or if people have solved it already, let me know. Say like, I'm done. Then I know where you're at, okay? Anyone done? No one. Okay, good. So then let's carry on. And if you're done, let me know. Just shout out, okay? Then we can come and take a look and see if how it's done. Yeah, I kind of refreshed it. So this line, 63 to 59 at least, 59 to 64. Okay. This one works. That's what this is for. This is actually this representation is, so I've set it so that I give it, let's say, 50 seconds to respond. And in 50 seconds, these are the 16 neuron nodes, right? So at first, because the input I want is the 1010 pattern, and I distorted it so that it becomes whatever that is, okay? And when I gave it this distorted partial Q, at first, this node number 10 was off when it should be on, right? So it was off, and then it did some calculation, and then it's still off, and then eventually, when it turned on, it reached some settling, and then it's stuck there. So this representation is what you are, like every time you print, it should change, yeah. And this is AD, the A differential, yeah. So I'm not sure if your A temp or whatever is printing something intermediate, and so it kind of gets stuck or maybe something like that. But I have in my code, if you take a look, I have this AD variable, and AD variable concatenates each time the system is updating its activation, and it settles, and what it looks like when it's trying to settle. Yeah. Okay, so maybe hopefully that can guide you in what you are trying to evaluate. Other questions? People finish? 有谁做完了吗? So you see, I think this is a critical step, because if we don't have this lab today, 你回去做那个 assignment 是不行。Okay. 有谁要问什么问题 then we can help you along the way. Yeah. Yeah, trading. So if I put it there, let's use this one and this. Testnet network takes in the trained weights, the distorted partial feature you want to retrieve the full feature from, the number of the response time window you allow it to respond. In this case right now it's like, let's say 50 seconds. Okay, you give it 50 seconds to respond. And then the threshold of the activation function that you want to modulate, and maybe the number of nodes you want to update at any given time, that you allow it to do computation at the speed of 1 node per second, or 2 nodes per second, sort of. Okay, and then it outputs AD, AT, E, HD, and F. F is very easy. Okay, F is just the failure flag. Means like the network, just couldn't settle. It keep going back and forth. The Hamming distance keep changing. And if you don't have a failure flag, right, the computer will run, and the CPU will burn and then melt. Okay, so this is to halt it. It gives it a failure flag, like did it halt or not. Okay, so it's not really so important, but it is just an indication. Hamming distance is an array, okay, of the Hamming distance is a scalar time course of like every time the network update, how is the Hamming distance greater than 0 or not, right? So you can see this Hamming distance is then used later to plot this one. So the HD is this line, this Hamming distance line, okay? So that tells you like over the 50 seconds, the network at first had Hamming distance 0, then it went to Hamming distance 1, then it went down to Hamming distance 0 again. You can see that's what this means, okay? And the Hamming distance is actually the Hamming distance relative to its previous state, okay? So it's not the Hamming distance relative to the target. It's this network's Hamming distance currently with the network's previous state, okay? And E is the energy, okay? Again, that's the time course, and that's used to plot the other blue line. AT, okay? AT is the, this one, output activation pattern. Like it's retrieved target response, okay? The final one. So AT is actually this last state here. Okay, this last vertical vector. Okay, so this is, although it's a heat map, you can imagine it's just vectors just add on to each other. Okay, and it is the last state is AT. Okay, AD is this whole thing. This whole array here is AD. So AD is an array. That I then use. I have to get it to output AD because I want to be able to visualize how the network, when I'm testing it, how the network is evolving. And that's AD. That's seen in AD. Okay? And if you go back to the code, you will see that AD, the definition, that's here. Okay? AD is every time the network updates an activity. When you ask it to retrieve, it will kind of do the computation. And every time, every round it does it, it logs in its state. So this round, this is my network state. I log it in. This round, A is my network state. And then I add it to AD. Then I do one more time. And I have a new network state, a new A. And then I add it to AD. A new network state, and I add it to AD. So eventually AD becomes a whole array of network state updates. So that's what that line is. And then this is returned in the testnet function. So we need all this because, well, you don't need it in a sense. Really all you want is A, right? And when we put A here, but later we call it AT, right? It doesn't matter because this is a definition. Definition, it will spit out whatever is relative to its own variable names. But when you call it in the global, you can always assign it another name, okay, depending on the way you use it. But the point here is that we need all these to evaluate, to visualize our model. Technically, you don't need it. If you don't care about evaluation, if you just want to use the model to give you an answer, then the answer is A. Okay? You only need that A because you want it to retrieve some memory, and the retrieving answer is A. Okay? All the other things, A, D, E, H, D, and F, are just kind of things for us to help us evaluate. That's all. Does that help? Yeah? So correct. So be aware of that. And this is important to note. And it will happen all the time. Because that's why I put things as definitions versus putting them as part of a code. When I put it as definition, what I'm saying 就是说我有这个 fundamental formula, and 它有它的那个 naming 的那个 method. So in here I call it WATUNI, okay? But when I use 这个 definition, 可能我是新的 WT or W123 or 其他的 W, 我有很多种的 W. But they are all the W that I have trained. 那我可以一直把它放在 W 的单位啊。Right? I don't have to always call it W. I just know that the first position should be an array of trained networks. In this case, the placeholder 是 W. But 以后可能我有一个 trained network 我叫 WT, 我有另外一个 trained network 可能我叫 WA, WB, and then 我就可以反正就是不同的 trained network. I can always just put it into this W placeholder. That's the power of using functions definitions. Okay? Yeah, so it's important to know, although the names change, they may actually be still the same thing. It's important to know that. Okay? Yeah. So for example, I can train a network and I call it Bob. Right? It doesn't matter. Bob is an array. So then next one I'll test Bob. Okay? Get it? Right? Yeah. I mean, for example, I will train this network. Let's see. Recursive, no. Learn, yes. And okay, so this is the default setting. And I want it to okay, I want to train Alice. Oops. Alice's brain. So I train Alice on this input array A, okay, which right now is this one, okay? And then, so I have Alice trained now, and now I will say I want to visualize Alice's brain. So let me so that I don't mess the code up, I do the comments. Okay, and I will say I want to see Alice's brain. And then now I want to test Alice's brain. Okay, so this is Alice. Right, it's different name, but I know absolutely it's this array that is in the function. As far as the function is concerned, is an array that is the form of W. Okay, but now I've just called it Alice when I use the function in a actual application, and this is Alice's brain. This is now Alice's brain. This is what Alice's brain looks like. This is how Alice performs when I give her a pattern of distortion factor 20% when testing her on pattern 3, etc. So you can think of it that way. Does that make sense? Okay. Any other questions? Feel free to raise up your hand whenever you encounter something that you need input from, okay? So if people are still working, I give you guys another 15 minutes and then you check in again, okay? Feel free to also step out if you need to. If you need to take a break or anything. Okay, spent a lot of time. Anyone? Has anyone finished the challenge, second challenge? You have? Or even if you're partially finished. Okay, let's share. Let's see what you have. See if play around with it. You are 中, so it's 这边是左还是右？是你们的右啦 right? Okay, so let me try it. 中 so let's say if I were to choose 这个 and then I say 是右中 Is this yours? Okay. All right. Wait.
Oh. Good. So.
Is it?
Hello.
Maybe the battery of the thing. Let's try this.
Yeah, this one much better.
Okay. Yeah,
so I'm just gonna refer to the first one, which is statistical evaluation. So we just want to record the accuracy and the sort of like number of iterations very stable, right? So for this mean, you of course need to do more simulations, and each simulation you need to store the final value of the Hamming distance and the mean number of iterations. So first of all, what's simple here is just adding the number of simulations, how many simulations we want. So in this case, I want 3 simulations. And everything here remains unchanged, but here we initiate, before we start the simulation, we just initiate 2 variables that stores the values. So logically, we should have 3 Hamming distances and 3 retrieval iterations. And this is just a for loop to run 1 simulation, 2nd simulation, 3 simulations. So the number of simulations you have, they just rerun it again. Now, I also randomize the test pattern. So it's just
each time.
Yeah.
Okay.
Each time it simulates with a different pattern, and this just is like there's 4, so you just do 0 to 3, and and then we just store like what's the pattern you want to, and then distorts the test pattern that we give it. Then actually the little bit of a change here is just that this is what HD history. This with a little bit of Gemini, so it's a little bit interesting. But basically, final Hamming distance is unchanged because already the original formula already have, so there's no need to modify it. So it just appends the last instance, the final Hamming distance 1, 2, 3, etc. Now the more interesting one is the number of steps where it stops. So based on the logic, it seems to be right. It's just that it lists like over 100 iterations. It calculates the Hamming distance, and it calculates the point at which your Hamming distance at time point A compared to the previous time point, there's no change there. So and if it detects that the Hamming distance is similar between these 2 time points, it stops the calculation, and then it sets that iteration as it calculates at the iteration at which it sort stabilizes, and then it just stores it into that variable, and then you just report it everything because you have all the variables, and then just run it everything. Okay. So this is simulation 1, simulation 2, simulation 3, and then it calculates over 3 simulations. The mean Hamming distance is 7, and then it requires like around 5 iterations to
okay.
So that's the current case. And then for input tokens, this is just the same thing, just changing the values.
Okay.
Yeah.
So like so if the key steps sort of jump ahead, but that one of the key steps is to set that loop over trials so that you can log. You want to, because you want to do statistical tests. You don't want to just run it one time, which is what we've been doing. Is we always run it one time and then we see the output, right? And then we run it again and then we see the output. So we qualitatively appreciate how the network performs. But as a scientist, we want to log all the data, right? And then after that, maybe we can have more data to then robustly and statistically validate that this model is performing, well or not well. Okay, so that's what this first statistical step that he did is Yongshen did is to do that, which was the first challenge. All right, and in a way that actually more difficult because that's like a bigger picture. That's why if you haven't got confident yet, the first step is actually challenge 2, which is to first try out on a different set of nodes first. But if you've got that down, then actually the statistical one is the more fundamental one, right? That you want to get it so that you can do many times. And if you do it many times, then you can go back to challenge 2 and then really evaluate whether the network performs well or not in the challenge 2 case. Does anybody get this code? What he's done in this step? And does it work? Does it work, Yongshen?
I'm just going to play with the numbers a little bit first.
And that's the thing. It's like, okay,
Yeah,
ideally we think that's what it's doing, and then like you have to try it to see if it works because maybe it doesn't. Maybe there's a bug we are not aware of.
I'm just going to do it parametrically. If distortion is 0, it should be correct all the time.
Yeah.
Yeah.
So then to really validate whether it works or not, obviously you have an idea of how the network should perform, right? You should have this expectation that, it should perform better or it should perform worse. And so if you do the statistics and the statistics sort of don't make sense to you, then obviously the first thing to suspect is, hey, did I code things wrongly? Some setup in my design, my architecture is a problem. If everything is really, really in order and it really doesn't perform well or doesn't perform as expected, then just like any other empirical experiment, you will be forced to conclude that maybe my hypothesis is wrong and I need, I need to revise my idea. So see the loop, see how this process is implemented as a simulation experiment. It is in many ways similar, or if you want to say exactly similar in the structure compared to empirical experiments. Okay? So that's the sort of framework. I do want to check one thing though. When you say you use Hamming distance, your Hamming distance is based on the final Hamming distance or the Hamming distances of each trial over time, over iterations.
So the final one is just the same one as the singular trial one. So it's the final Hamming distance.
Okay, but that's not true, right? Look at the heat map. So you look at the node heat map.
Yep.
You can see already at iteration 1 and iteration 10 or so, look at this heat map on this here.
Yeah.
Maybe I go here.
Okay.
Yeah, so here, look at this heat map here, right?
Mm-hmm.
So you can see here, there's a change, right? And so the Hamming distance here and here will be different. Will be more than 0.
Yeah.
And then even here as well. And then maybe here and around here, the Hamming distance will be back to 0.
Yeah.
Because this state and the previous state are the same. Even though it's wrong, right? Assuming this is wrong, then, but the Hamming distance is the same. Means the network is the Hamming distance of this network state and its previous state is 0, but the network is in a wrong state, right? Yeah, and that's why we have we want the energy to settle for at least how many trials first before we accept the answer. So the Hamming distance at each iteration is not the final answer. It is actually when the network's energy has come down to a level and the energy doesn't go down anymore for some period of time, that is the answer. Okay, because it can still be in doubt. The Hamming distance may be the same. It's like, think of it this way. Right now, my brain may be thinking, wait, it must be cat. Is it a cat? It's cat, right? So it's like cat, 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 but actually the answer is dog, right? So it's like I'm stuck in cat for a few milliseconds, but then maybe at some point, oh, wait, no, it's dog, right? And then, yeah, dog is correct, so it's lower. Okay, so that happens, right? In your thought cycles, that's what that is. It's like maybe your computation is stuck in some intermediate one, and it's stuck there for a while, so the Hamming distances are the same, but it's not yet the lowest possible energy, or at least in that instance, compared to the probe and the memory. Okay, so actually I would suggest to use energy as the RT equivalent rather than the Hamming distance change. Okay, think about that. Okay, so for example, if I were to switch back to mine, like let's see, go check your Hamming distance plot, because you see the Hamming distance does go up and come back down again. It's not like it goes down and then it never comes back up ever, but the energy always goes down. Okay, and then the energy, when it is really, really at its minimum possible, it may be wrong, but at least in that trial, the energy doesn't go down anymore, then it's never going to go down anymore. Okay, but the Hamming distance might still fluctuate. And you can see the Hamming distance fluctuation corresponds to each step that the energy goes down. So for this trial, right, the Hamming distance changed and the energy went down. And then it kind of stayed put again, and then it changed again, and then it went down some more, and then it changed again, and then it kind of stayed stable. Okay, so actually the energy change and Hamming distance change corresponds. But the Hamming distance being 0 or not 0 is never like a stable thing in the sense of the principle of it. Okay, it is more about energy. So, but you need both, because the final Hamming distance with respect to the correct answer, right, could be 0 or could be not 0. The system could be wrong right at the end. Even though it's settled on its answer using the energy, its answer could still be wrong. And so you still need that yes for accuracy. Okay? Got it? Yeah. So that's something to, things happen. See, look at it in this case, see? It kept fluctuating and fluctuating, and the energy, it fluctuates even, but then the energy may not change. And then they decide that, well, okay, the energy doesn't change even though I change, so, I'm just going to keep it that way, right? Okay, yeah. So the way I did it is like, for me at least, the same statistical thing is I did 6 loops, and out of the 6 times, 4 times the Hamming distance was 0, 2 times the Hamming distance was 6. So the average would be like, what's the average? I don't know. Okay, some average between 0 and 6 is the accuracy of this network, okay, for that problem. And it took about between 0 to 31. Actually, 0 should be not counted. It should be 13, because 0 is the starting thing, okay? So 13 to 31 iterations, 13 to 89, no, 10 to 89, a range of 10 to 89 iterations every time it runs, okay? Then you can try, make it more serious, make it more perturbed. Maybe the iterations will increase, etc. So these are, and since these are just a string of numbers, you know how to do statistics. You can calculate mean, standard deviation, and that will be your statistics, okay? So that's how you do the statistical evaluation, okay? Yeah, okay, anyone else had different versions or different steps to share? Anyone has a problem to share, like you're stuck, and maybe people have some idea, or we can discuss it. Anyone want to talk about your problem? Actually, that's more informative. If you have a problem, you're stuck, and you want to poll the 大群组。
So I just have a question about the Hopfield app, the simulation part about variable ni.
Yes.
What actually does it like?
Oh,
Yeah.
the number of nodes to update at a time. So you've got 4 here, which
Okay.
and ni only applies during retrieval, right? Doesn't apply during encoding. Encoding is parallel, which is very natural, right? It is, we are always encoding everything instantaneously. But retrieval is asynchronous. Actually, Hopfield uses that term because you are focusing on some sub-features at any given time in your retrieval performance, okay? Whereas when you are encoding, you are not really choosing what to focus on. I mean, yes, you might be distracted, but that's different from, let's say, your conscious control, okay? So in this case, it's sort of like a semi-conscious control parameter. So for example, if you are updating only 1 unit at a time for retrieval, it means like, I gave you cat, I gave you tail, and I want you to retrieve cat, okay? So what you are doing is, okay, you gave me tail, let me focus on the eye feature, does it have 2 eyes? Oh yeah, doesn't have 2 eyes or has 2 eyes. Then now let me switch to another node. Does it have fur? Is it a tree? And then does it have a tail? Like that. So if I only update 1 node at a time, it means in our simulation, it means I focus on 1 dimension at a time to update or not. In terms of my activity to flag that it is supposed to be yes or no, okay? If I do 2 or 3 or 4, it means at one time I focus on, does it have an eye and does it have fur? Like that, to retrieve my memory trace. Does that make sense?
So in this case, because it's just binary, logically shouldn't be more than 1, right? Or not necessarily?
Well, I would say this is a hyperparameter in a sense that we don't know. In a sense, as a code it works. Obviously you see. But does it reflect what we do? That's another question. And so then that's why you have an empirical simulation.
Yeah, I asked that because I tried making the number from 1, 2, 4 to all the way to 16.
You can do 16, yes.
And there's no consistent pattern to it. Like distortion increase, of course, the hemispheres will naturally be increasing, but no, doesn't seem to be very
in this case,
observable.
In this scenario, maybe change the tokens to encode. Maybe 16 is not significant enough. Maybe you need a 50, 64 node memory, and then that maybe many things to try. And exactly right. The way to test and find out is to try all this. And since it's code, you don't have to spend money to collect subject feed, collect data. just type a loop, and then you've got all the tens of thousands of subjects data. And then you can do the statistical test. You see so this is addictive to me, right? This is why I would do simulations sometimes, because it's like, I can answer some interesting questions without even actually having to collect data. Whether that's real or not, that's a different question, but you use your sort of common sense to say, yeah, maybe that's sort of real, and of course we know it's a simulation, we still have to collect real data, but that's the fun, that's the joy of trying this out, and then seeing what these parameters mean and how breaking them affects the performance. It's fun, right? I mean, I don't know, I think it's fun. I think it's part of learning and kind of working with your ideas and implementing into the code, and then seeing how that cycle goes. Yeah. Other questions? Problems? I mean, I really hope that you guys can use this course time to get over critical hurdles because, and then I'll go on to the thing, yeah, we have time. I'll go on to the assignment 1 next because if you don't get on past this hurdle here, it'll be, and then you're on your own to do assignment 1, it'll be a bit more difficult. Of course, you can post discussion in email, that's fine, but this will be the best time to make sure that you can use the code to do these things. Or at least that you have an idea, you know, right? And then if you go back, you know, you clean things up, you should be okay. Okay, so let me, any other, yeah? Mm-hmm. U? Yeah. Okay, let me switch it back to mine.
Because we kept getting 0 Hamming distance when we set it to 0, and when we set it to other things, it started to have, you know, Hamming distance fluctuation stuff. So I want to make sure why, even if you set it to like negative, you get Hamming distance, but when you set it to 0, it just gets nothing. Like it's just flat.
If your code is always giving flat and then you have distortions and stuff, I will go back and check whether the code there's some bug first. It's just 2 separate things, okay? So first, if you are finding that your Hamming distance result, like this one, no matter what it is, it's always 0, and you have distortions, you would expect if you have distortions, the network, especially if you increase the distortion to, let's say, 50%, then your Hamming distance shouldn't always be 0, correct? Right? Okay, so just check that. Make sure that at least that is working first. If that is working okay, all right, now, then what does the U do? Then you modulate the U parameter, okay? Now, the U, in terms of the definition, let's go back to the definition. U is implemented in the testnet function, okay? Oh, and by the way, I call it testnet Hopfield. You know, feel free to call it whatever you want. Okay, this is just my, I mean, I know everyone's copying my code and stuff, but you know, feel free to creatively create entirely your own Hopfield network, okay? All right, you might do it better than me, okay? Seriously, this is just my way because you know I fixed it. It could be that if I do it next year, it'll be a different name also. So, okay, so U is used in the retrieval function in the test phase, and if you go to the code, you'll see it's implemented here, line 63 in this case, okay? And what that means is that we know what the threshold is, right, in the binary activation function, right? If the sum of the modulated inputs is greater than U, then that unit is active. If it is less than U, then that unit is set to 0. Okay, so if so think about then at this point, all the W's, if we train the W 1 time, okay, and it is using the Walsh function, okay, if we train the W 1 time and it is using the Walsh function, the W looks like that, okay, as we talked about before. Since it's Walsh functions, it's very pretty. It's like left is all on, right is all off, then on, off in sets of 4, then in sets of 2, then every other, right? Very pretty, the Walsh function, that one. Where is it? Oh wait, no, it's here. No, it's not. It's here. There you go. Yeah, very pretty, right? So this geometry or like pattern that we visually see, but actually is meaningless, right? And so far as the computer is concerned, that leads to this weights pattern. Okay, think about it in terms of the when you are talking about, now I have a input that is distorted, and I pass it through this weights matrix. This weight matrix is maximum, minimum, because I only train it once, maximum, minimum will be plus minus 4, because I have 4 different tokens. So every time it's the same, I plus 1. Every time it's different, I minus 1, right? So the maximum I can get is plus 4, or minimum I can get is minus 4. And because it's Walsh functions, they all left, right is very, in terms of the neurons, you can see it very nice. This one is very far away, right, from the 0, and then there's this nice, like, kind of diagonal line there. And then also, there's kind of all these patterns that you can see, very geometric. This is going to always be like that because of the functions, the way the learning function works, and the Walsh function patterns. Now, go back to the U. So U is the threshold, and they're comparing it against W times input. W is always plus minus 4, the range. So reasonably, at least in here, the average is 0, correct? So when we set U to be 0, then, and given that the input is either 1 or 0, right? That means it's either going to be above 0 or below 0 with a maximum of 4 or even 8 or 16 or whatever, because it's going to be plus 4 times 1, plus 4 times 0, plus 4 times 1, plus, and then plus 2 times 1, plus 1 times 1, all that added up together, right? You are going to be maximum, let's say, okay, so let's say every weight is plus 4 and every node is 1, then the maximum would be 4 times 16, which is whatever that number is, okay? 64. So the maximum is 64. And the minimum is minus 64. The maximum possible is 64. The minimum possible is minus 64. The middle being U, 0. If I make U positive, then I make it so that it is very hard. My range of sum for me to make this node active has to be greater than U, correct? But my weights are all minus 4 to plus 4, which means minus 64 to plus 64, possible range. So if I make U to be like 24, that means I have now like from 0 to 24 plus to minus 64. That range, the unit won't be active. Understand? Does that make sense? Okay. I can make it worse. I can make the U to be like 63. And then that means that only one possible case where the unit will be on is if all the inputs are 1 and all the weights are plus 4, which is not the case. So now no units will ever be on. Okay? Mathematically, think about that. Okay? So then by raising U means I'm making it harder for the nodes to become on during retrieval. And by making U lower, I'm making it easier for the nodes to become on. Okay? So biologically, making U higher means actually to inhibit. And making U lower means actually to excite. Okay, so just think of that. Does that make sense, what U is?
So you said a really low threshold.
Actually, it's more active.
Yeah, it's more active, and then the Hamming distance becomes stable.
How that relates to Hamming distance, that is the other question, right? I'm only telling you that when I raise or lower U, I make the activity more or less likely. But I actually don't know whether how that affects the model's ability to retrieve. Like, how accurate would it be and how fast would it be? I don't really have an intuition of that right now. I mean, I do, but I haven't, go try it out and see what happens. My intuition is, and I might be wrong here, is if you make it too active, it will settle too fast, but it could be wrong a lot of times, and it will be very, 就有点 like 冲动, right? Okay, that's the answer. It's a cat, it's a dog, it's a cat, it's a dog. But then it's never right, but it's just thinking that it's right or wrong. So it will do it more times and be wrong more times. But it might be right more times as well. So maybe the accuracy, average accuracy, maybe it doesn't change, but maybe the response time will be faster or something like that, maybe. But then if you make it like not more conservative, don't be so active, it might take longer to settle, maybe. Yeah, I'm not sure. So in terms of accuracy and all, there might be an inverted U shape, like where it might be optimal level, and it turned out the optimal level might be where you set a threshold to 0. Okay? Because then it's not bias, right? There's no bias. Well, if anything, you have some bias. Here's another thing. One of the challenges, I think, in challenge, last one. So yeah, let's take a look at the other challenges, okay? Because up to this point, we've always started with the weights being scalar 0, okay? What if you start the weights being random weights? Not all 0, but some plus minus 1, whatever, okay? So for example, if I set the W to be a random array at the start, then I train it. Now, it's not a guarantee that the range would definitely be between minus plus 64 activity, or that the weights are going to be plus minus 4, because the random thing could be, or it's already plus 4, some of the weights. If I train it, somehow it becomes plus 8, or whatever. Okay? Now, how does that affect the memory? Which is more realistic, because we never come to a scene unbiased. We always come with some preconceived training, preconceived idea. Okay, so how does that affect? Then, challenge 6, try to change its memory. Okay, it's already learned cat, dog, mouse. Can you now tell it that, oh no, actually there's no cat, dog, mouse. There's only, stars and moons and whatever. Okay, can that be done? Can you make it forget? What is forgetting? Okay? You see, these are very interesting questions. Just with this simple thing, see how many psychological concepts you are sort of trying to model and challenge and validate here. Yeah? It's a lot to play with. Okay? And implications of that, because you can mathematically actually formalize this and sort of control it in that sense. Okay? So that is about the weights and the thresholds. So that's a great question. Any other questions about that? So the flip side of it, so that's about weights and the thresholds. What about different types of inputs? We sort of touched on it, so we had Walsh functions as the input. We have non-Walsh functions, okay? Different sets of inputs here. What about if we had not just 4 inputs? What if we have 8 different items to learn? Not just cat, dog, tree, mouse, but also orange, apple, banana, pear. As part of all the things we need to encode. Okay? You can try that, all right? And so far, we only talk about 16 features. What if we use, therefore, if we have 8 tokens, do we need 32 features? Do we need 64 features? Or actually, is it that, do we really need 16 features? Is it that only 8 features, an 8-bit word, is sufficient to encode 8 items? Or, or even 16 items, okay? So in terms of the input, that also can be played with. And also identity array. You know what's identity? Identity would be, if it is an 8 by 16, identity would be like, this is 1, everything is 0. Then the next row is this 0, then 1, then everything is 0. And 0, 0, 1, 0, 0, 0, 1, So that's identity matrix, right? Why is it so special? Identity matrix is exactly orthogonal, correct? Every row is independent from every other row, for sure, okay? And there's no overlap at all. And this is interesting because when I give you information that is exactly, categorically different, theoretically we should be able, that's the best way for us to learn something, where there is no need to overlap. Okay, there's no overlapping thing. You know, just something to play with. Okay, is it overkill? Then, all right. So this some other steps. So these challenges sort of give you that kind of space to play with. Any questions about these challenges? You have? No?
Just one question, because if we were to be like a little bit more creative with like the Hopfield, the function, the 5 variables. Let's say I want to add like a 6 or 7 thing that it will encode to make it a little bit more to maybe extract a variable that I need. How should we go about like to just adding that
adding more tokens to encode, you mean?
Yeah. No tokens. The Hopfield function has, currently we have the number of iterations, Hamming distance, etc. Right? Let's say I add like another thing to it.
Another evaluation metric. Okay. So if you want to do you want to evaluate for retrieval or for encoding? Probably retrieval.
Retrieval,
okay. So, but you can do it in encoding too, but I mean, it will be the same principle. But let's say you want to have another evaluator at about the retrieval performance, then the way is you go back to the definition, the testnet Hopfield, okay? Then initialize more evaluators if you want. So for me, the evaluators are E, energy, HD, Hamming distance, and AD, the holding activation array, which is so AD is like fMRI. So I'm scanning, as you are doing the task, I'm scanning you, and I'm seeing how your brain changes each time, right? Okay, so those will be some of my evaluators. If you want other, and so if you, and I have to initialize them, right? So I have to set them first. Then you have to embed in your code each time how you want this to be recorded. So for example, E is just appending. For each time, I just append the state's energy, and then another change in energy, so I append again, and then I change again, and I continually extend E. HD as well. Every time the Hamming distance, I extend HD. That's why at the end, when it spits out E and HD, it's a time course. Okay. Similarly, AD, it's a concatenation. Which is appending of an array. Okay. So similarly, does that make sense? So if you have another thing you want to evaluate, you can initialize it and then see in your code where you want to slot it in. Is it something that needs to append, or is it something that, no, after I run it all, I have one final summary? Those are many different kinds of evaluators. So you can do it here, or it could, and so this is what we call online evaluation, okay, because it is inside the retrieval code. It could be offline evaluation, which is after it's done its retrieval, it spits out something, and then you encode that externally, offline. Yeah, so those are the various ways. Yeah, you definitely need to think about that, because when you do backprop, there are similar things, but there might be other evaluators you want to use, you want to encode as well. Okay. Other questions? Okay, you're going to need this. So I want to go through the statistical loop again. You're going to need this, and then I'll talk about assignment 1, okay? So as Yongshen pointed out, and I have embedded it in my code now, so you can copy it or model after it if you want, okay? But apart from just I run it one time and I see it, I need to loop it many times and then log statistical performance values over. Let's say I run my model. In this case, I run it for 5 trials, okay? Now I want to collect its performance. Let's do 10 trials. Let's see how it goes, okay? Oh, didn't like that. I think I changed something, didn't I? Yeah. Oh. If yes, report string not callable. Okay, I see. Let's just not be ambitious for the moment. Did I change something? Delete this. I see. That's what it is. Okay. Yeah. I need to run the definition again. This, then do this. Okay, so I've told it to run. So now I'm a scientist, right? And I want to test Hopfield. I collect 10 people's data. So I should call this number of subjects, not number of trials, okay? Or a subject doing it 10 times, okay? So then I have, see, this subject's performance. So this is, let's call him Bob. Bob's brain looks like that, okay? And Bob's first trial got the answer wrong. Second, and this is Bob's fMRI brain over time, for when he tried to answer this question. Then I asked Bob again. This time he got it right, and then this is his brain activity, okay? And then got it wrong again, and this is brain activity. Got it sort of right, and then right again, and wrong, and whatever, okay? So this is many, many trials of Bob's performance. And then also at each trial, the energy, it's like I got the brain activity, but I summarized the brain activity index, okay? So this all these. So I did it 10 times. So Bob answered 10 questions, okay? And at the end of 10 questions, Bob's performance, I have 10 of it, or at least 9, the first few, okay? And that's reaction time, his accuracy and his reaction time. Okay, so I need this because for assignment 1, it's going to ask you to create a Hopfield network and then run it more than one time, and each time log in some values, and then kind of from there, you have a fairer picture of is the network performing statistically different from different conditions, in different conditions. So how do we do that? Here, you can take a look at the code on your own time, but similar to what I just said. It's another way of saying you want to evaluate, and if you want to evaluate anything, you need to initiate your evaluators. So for me, I initiate a time course of Hamming distance, so I call it HDT, not just HD now, okay? And a time course of minimum E, the minimum energy, which for me would be when the energy is minimum, when did the network reach that lowest energy point? So the minimum E time course, okay? And the minimum E for me, I calculated it using a function that I embedded. So I created a new definition called stats. And if we go back to the definitions, this is the new definition I have called stats, okay? And this only pertains to when I want to do statistics. And in stats takes the Bob's answer, AT, the correct answer, A, then I can calculate accuracy, right? Whether Bob's answer is the same as A or not. And how do I calculate it? Well, at that time, what is the Hamming distance between Bob's answer and the correct answer? And I also know the RT, how long did Bob take, okay, to settle on the answer? That is the minimum. Okay, so E is the energy, that time course, right? Time course reaches a minimum and doesn't change at some point. I want to know when that happened. So I asked the code, where in this whole time course is there the minimum value of the time course. So that's line 158, if you understand, right? It is the minimum of where E is its minimum. Because the minimum of where E is minimum is like, so maybe 0, 1, 2, 3 iteration, E is still very high. And then at iteration 10, it's at its minimum. And if it is at its minimum at 10, it will always be at its minimum at 11, 12, 13 onwards, right? So I have, if I ask where is E the minimum, the answer will be 10, 11, 12, 13 to whatever. The minimum of that is the first instance when E reached the minimum. Okay, so minimum of where E is minimum. And that will be my reaction time, sort of, my reaction time equivalent. And I log that as an instance, but in this definition, but I accumulate that in the code, in the scientist code. I accumulate that by using the extent, okay? I append that as a whole time course, or at least as a whole vector, and that's why I can get this, like each trial's performance, and then I can use SPSS to calculate those stupid, use Python, right? So use the mean and the standard deviation, and I can do t-tests. Let's say I now have this subject, this is Bob, right? I can then run Alice or Charlie, or I can do many subjects, and then I can compare Bob and Alice, Charlie and David, or whoever, okay? So this is how to do sort of stats given your base code. This is the complete package, okay, of how we would validate and run a simulation. Okay, any question about that? Okay, so you have the code. Feel free to go back and take a look if you're not sure. Okay, but I hope you get it. Okay, I want to quickly just show you assignment 1, and then that's it for today. Okay, and I hope that's not too much. All right, that's why you need time to sit down and code and kind of absorb things and work through practical stuff. Otherwise, it's very hard.